So when you have a butane lighter and you light it, there's only a small amount of butane gas that's released from that lighter, and it combines with a lot of oxygen present in the air. So we don't put any kind of number on the oxygen present in air, so we call that excess. So that's considered excess because there's so much more available than is required for the reaction, which means that butane is our limiting reactant. So butane controls the amount of products that are produced in the reaction. We have to use up all of our butane to create the maximum amount of products, but we'll still have tons of oxygen left over because it's just floating around in the air. We can't use up all the oxygen in the air, no matter how hard we try, unless you're in a sealed container and you're suffocating. But never mind that. So when the reaction is complete, the limiting reactant or reagent, sometimes you'll hear limiting reagent, is completely consumed. So whatever amount of our limiting reactant, in this case butane, you had to start with is all gone. So you end up with 0 butane. And you'll still have some of your excess reactant left over because you had more than you needed. All right, so let's go back to our idea of thinking of balanced reactions as recipes. So this should be more familiar to you guys, and I'm going to try to make everything that we learn as far as stoichiometry in terms of some things that are more familiar to make it less scary and intimidating. So imagine you're baking a cake that requires 1 egg. So your recipe says 1 egg. You only have 1 egg in your fridge. So I guess you ate all the other ones in some omelets or something. So if you only have 1 egg, but you have a lot of all the other things, then the egg is your limiting ingredient. If you only have 1 egg and your recipe calls for 1 egg, you can only make 1 cake before you run out of eggs. You will, however, have some of the excess ingredients left over. So say you had a whole bag of flour and a whole bag of sugar, you'll have some flour and sugar left over after you bake your 1 cake. All right, so let's test it out. So let's make some more sandwiches. So as a reminder, my perfect BLT recipe contains 2 slices of bread, 1 tomato, 3 leaves of lettuce, and 4 bacon strips. In our kitchen right now, we have 15 slices of bread, 10 tomatoes, a head of lettuce that contains 40 leaves of lettuce, and a pack of 24 bacon strips. So we have to use our recipe to find out which one of those is our limiting ingredient. All right, so I'm going to introduce you to something that will be very helpful in this process, the ICF table. So ICF stands for initial, change, final. Sorry, I crossed out change. I meant to underline it. All right, so you're going to write what you started with in the initial row. So we started with 15 slices of bread, 10 tomatoes, 40 leaves of lettuce in our head of lettuce, 24 strips of bacon, and we don't have any BLTs when we start. We're going to assemble our BLTs over time. So we want to write our ingredient ratios. We got these from the last video, so I'm just going to copy them over here. So our recipe tells us that we need 2 pieces of bread for 1 BLT. So that's our ingredient ratio for bread. We needed 1 tomato for 1 BLT. That's our ingredient ratio for tomatoes. We needed 3 leaves of lettuce for 1 BLT. That's our ingredient ratio for lettuce. And we need 4 bacon strips for 1 BLT. And that's our bacon ingredient ratio. So when we use these ratios and the amount of each ingredient that we had to start with, so we multiply by our ratio so that we can cancel out bread, tomatoes, lettuce, and bacon in all of our equations. And we end up with, we could make 7.5 BLTs if we were only worried about bread. We could make 10 BLTs if we were only worried about tomatoes. We could make 13.3 BLTs if we were only worried about lettuce. But we can only make 6 BLTs with the amount of bacon we have. So bacon is our limiting ingredient. We run out of bacon first. So what we're going to do next is fill out the rest of our ICF table. So the change, we're going to calculate the change based on the amount of BLTs we can make with bacon. So we use up all of our bacon and we don't have any left to make 6 perfect BLTs. So now we reverse our ingredient ratios to find out how much of each ingredient we use to make 6 BLTs. So we can cancel out our BLTs and we end up with 12 pieces of bread in our 6 BLTs, 6 tomatoes in our 6 BLTs, and 18 leaves of lettuce in our 6 BLTs. And that's what goes in the change row of our ICF table. So then we ended up with 0 strips of bacon left over, but our other ingredients are all excess ingredients. So you subtract the amount that was required to make 6 BLTs from what you started with to find out how much of your excess ingredients you have left over. Okay? So you should be very familiar with the ICF table by the time that we're done with this video. All right. So here are the steps for solving a limiting reactant problem with chemical reactants and products. You want to write and balance the equation first. Always balance the equation first. You can't have the proper recipe without a balanced equation. All right, so then whatever they give you in the question, that known mass, you're going to convert into moles because we always have to use moles in our recipe. Then you're going to use the mole ratios to find out which reactant is limiting by doing what we did with the sandwiches. You need to find out how much product you can make using each of your reactants, and the one that makes the least amount of product is going to be your limiting reactant. And finally, you want to take that amount of product that you get from the limiting reagent or reactant and convert that from moles to grams using the molar mass to end up with the grams of the desired product that you were able to produce. All right, so let's try it. We'll make some more fireworks. Again, barium sulfate reacts with hydrochloric acid to form barium chloride and sulfuric acid. We have 20 grams of barium sulfate, and this time I'm telling you that we have 50 grams of hydrochloric acid. So how much barium chloride do we get, and which one of those is our limiting reactant? All right, so we're going to use our ICF tables again. I put all of the molar masses at the top of the table to help us out. So our first step, step 1, is to balance the equation. So barium sulfate reacts with hydrochloric acid to make barium chloride and sulfuric acid. So we have 1 barium on the left and 1 barium on the right. So that's fine. We have 1 sulfur on the left and 1 sulfur on the right. So that's fine. Let's skip over to chlorine. We have 1 chlorine on the left and 2 chlorines on the right. So there's one place where we can balance. So if we have 2 hydrochloric acids instead, now we'll have 2 chlorines on the left and 2 chlorines on the right. Okay, let's check our other atoms. So we have 4 oxygens from our sulfate ion on the left and only 4 oxygens from our sulfate ion on the right, so that's good. And lastly, hydrogen. We have 2 hydrogens because we have 2 hydrochloric acids on the left, and we have 2 hydrogens from our sulfuric acid on the right. So that is our balanced equation. We just needed 2 hydrochloric acid molecules to balance our reaction. So we filled out our initial row with what was given in the question. And now we can convert the known masses of substances to moles. So we started with 20 grams of barium sulfate, and when we multiply by the molar mass, we can cancel out grams. Sorry, we divide by the molar mass. I apologize. When we divide by the molar mass, that inverts our units, so we can cancel out grams and end up with 0.0857 moles of barium sulfate. And that's what we put in our initial moles row of our ICF table. All right, and we started with 50 grams of hydrochloric acid. So we, again, divide by the molar mass to cancel out grams, and we end up with 1.37 moles of hydrochloric acid, which we put in our table. So our products, we still have 0 of each of our products, grams or moles, doesn't matter which unit when you have 0. It's because we didn't do our reaction yet. All right. Step 3, we want to use our mole ratios to determine which reactant is limiting. So our mole ratios come from the balanced reaction. So barium sulfate and barium chloride are 1 to 1. So we have the moles of barium sulfate canceled out, and we end up with the same number of moles of barium chloride as we had of barium sulfate because it's a 1 to 1 ratio. So that means we can make 0.0857 moles of barium chloride when we have 0.0857 moles of barium sulfate. So how much can we make from the hydrochloric acid? So hydrochloric acid has 2 moles of hydrochloric acid in our balanced reaction. So that means that our mole ratio is 2 moles of hydrochloric acid per 1 mole of barium chloride. So when we multiply by that mole ratio, we cancel out our moles of hydrochloric acid, and we find out that we can make 0.85 moles of barium chloride if we only worry about hydrochloric acid. So that is a much larger number than the number we got from our barium sulfate. So that tells us that barium sulfate is our limiting reactant. We'll run out of barium sulfate long before we run out of hydrochloric acid. So assume that we use all of our barium sulfate to make barium chloride. So our change row uses all of our moles of barium chloride so that we end up with 0 moles of barium chloride. And we end up with the same number of moles of barium sulfate. We end up with the same number of moles of barium chloride as we had of barium sulfate because of that 1 to 1 mole ratio. So if we want to finish up the problem, we want to convert from moles to grams of our desired product using the molar mass. So we were able to make 0.057 moles of barium chloride, and when we multiply by the molar mass, we can cancel out our moles, and we end up with 17.8 grams of barium chloride and 0 grams of barium sulfate left over because that was our limiting reactant. All right, so how do you feel? Pretty good, right? ICF tables are very, very helpful in organizing all of your data. So to practice, I would suggest you guys fill out the remaining columns of this table. Even though it wasn't required in our question, it'll be good practice to find out what's left over of hydrochloric acid and how much sulfuric acid was produced. All right, moving on. So you can also see this concept in the laboratory, which you can't this semester, but in the future you will be able to. For example, consider the reaction of iron chloride with sodium hydroxide in this reaction here that is balanced for you. If a student starts with 50 grams of iron chloride and adds sodium hydroxide in 1 gram increments, as shown in this plot, we can plot the mass of the iron hydroxide that is made as a function of the mass of sodium hydroxide that is added. So as you can see, it starts to plateau at 37 grams of sodium hydroxide. That is because that is where we change from having sodium hydroxide as our limiting reactant to having iron chloride as our limiting reactant. So at this point right here, we have the same amount of sodium hydroxide and iron chloride being consumed in the reaction. So at that point right there, both of them are limiting reactants. Up to that point, the amount of iron hydroxide that was produced was dependent on the sodium hydroxide you started with. So that is where the sodium hydroxide was limiting. After that point is where the iron chloride becomes limiting because we're no longer, so our iron hydroxide production is no longer controlled by the mass of sodium hydroxide. It is now controlled by the mass of iron chloride. So unless you add more iron chloride to your reaction, your amount of iron hydroxide is not going to change because iron chloride is now your limit reactant and you have used it all up. All right. So now moving on to more experimental, more laboratory-based topics. When chemists perform experiments to make a compound, when we synthesize a compound, it's very rare that the amount of materials produced is equal to what you predict based on stoichiometry. So lots of things go wrong. You can spill your reaction and lose some of your reactants and products. You could have a precipitate, so a solid that you're forming, and then when you filter it, some of the solid goes through the filter and you aren't able to capture all of it. You can also have a percent yield that is higher than 100%. So you can actually have a higher amount of material produced than was predicted if you are including things that are not the product that you wanted. So if you end up with a white solid and that the mass of that white solid includes both sodium chloride and potassium chloride, for example, your yield of 1 is going to be higher than 100% because your mixture is a greater mass than just the mass of the two parts. You could also have more than 100% if your product is not fully dry and you take the mass and that mass includes some water that is still in your solid. So there's lots and lots of things that can go wrong or that can be unavoidable when you are synthesizing a compound. So the amount of materials produced is almost never the amount that was predicted based on stoichiometry. So the distinction between those ends up being this percent yield that we're going to calculate. So the percent yield is made up of the experimental yield, or actual yield, what you are able to weigh on a balance in the laboratory. And the theoretical yield is what you would calculate from your stoichiometric calculations that we've done in this and the last lecture video. So when you report the success of the chemical synthesis, you report it as a percent yield. You take the experimental yield and divide by the theoretical yield and multiply by 100 to get it into a percent. So let's practice. So the steps for solving a percent yield problem is the same. So the same first few steps as our limiting reactant problem. You want to write and balance the equation. You still need to balance the equation first and foremost. You want to convert known masses to moles. You want to use mole ratios to find out which one of your reactants is limiting. And you want to find the amount of product that's made by that limiting reactant and convert it from moles to grams so that you can get your theoretical yield. So the theoretical yield was the final answer in our previous problem. So the amount of product that you make from your limiting reactant is your theoretical yield. So then the question will give you the experimental yield, or if you're in the library, the experimental yield will be what you are able to produce in the lab. And by that real yield, so that you're going to divide, I'm sorry, I have these mixed up. You want to divide the experimental yield by the theoretical yield. Just keep this equation in mind. And then multiply 100 to get your percent yield. All right, so let's do it. Consider the reaction of chlorine with water to form hydrochloric acid and hydrogen chlorate. So we start with 4.35 grams of water, and we react with excess Cl2. So that in our question is telling us that we don't need to worry about how much Cl2. We are told, basically, in the question that water is our limiting reactant. And we are able to isolate 10.8 grams of hydrochloric acid, which is our experimental yield. So this they gave you because you measure it yourself in the lab. All right, so what's our percent yield? So step one is always to balance the equation. So let's see what we've got. So what should we balance first? Chlorine shows up in 3 of our reactant product compounds. Hydrogen shows up in 3 as well. So oxygen only shows up in 1. So I'm going to start with oxygen. We always start with the one that shows up the least in our reactants and products. So on the left, we have 1 oxygen atom, and on the right, we have 3 oxygen atoms. So I'm going to start by making 3 waters so that now we have 3 oxygen atoms on both sides. All right, so it doesn't matter which one you pick next. I'm going to go with hydrogen. So we have 3 water molecules, which means we have 6 hydrogen atoms on the left. And on the right, we have 1 hydrogen atom in this hydrogen chlorate and 1 in our hydrochloric acid. So we only have 2 hydrogens on the right. So we need to balance that. So we don't want to, because we already have our oxygens balanced. So let's change hydrochloric acid. So we need to get 6 hydrogens. So if we make this a 5, then we have 5 hydrogens from hydrochloric acid and 1 from our hydrogen chlorate, which gives us, 6 total, which balances our hydrogens. All right, so finally, we need to balance our chlorines. So on the left, we have 2 from chlorine gas. It's one of our diatomic gases. And on the right, we have 5 from our HCl, thanks to our subscript. So, and we have 1 from our hydrogen chlorate. So that means we have 6 chlorines on the right. So this is the easy part to balance. Now, if we make 3 chlorine gases, that 3 times 2 gives us 6 chlorine atoms. So now we are all balanced. 3, 3, 5, and 1. So I'm going to erase that. I'll rewrite it without all the messy stuff at the bottom. And now let's keep going. So we start with 4.35 grams of water. And we have excess chlorine gas, so water is our limiting reactant. So let's find out how many moles of water we have by dividing by the molar mass. Cancel out our grams, and we end up with 0.242 moles of water. All right, and now we're going to use our mole ratio. So again, you could do this in one step. I'll do it in several this time. Sorry, that's a 2. Moles of water. And our mole ratio is going to be 3 to 5 for HCl. So we put 5 moles of HCl on top and 3 moles of water on the bottom from our balanced reaction. So we cancel out moles of water and we end up with 0.403 moles of HCl. All right, so next, I'm going to use again 0.403 moles of HCl. We want to find grams so that we can use that as our theoretical yield and divide our 10.8, our experimental yield, by that. Okay, so we are going to multiply by the molar mass of HCl. Chlorine on the periodic table is 35.45 grams per mole, and hydrogen is 1.01. So together, the molar mass is 36.46 grams per mole for hydrochloric acid. So we cancel out our moles, and we end up with 14.685 grams as our theoretical yield. All right, so this is our experimental yield. And our percent yield is going to be the experimental divided by the theoretical times 100. So 10.8 grams divided by 14.685 grams times 100. And our answer, our final answer, is 73.5% yield. So our reaction was 73.5% successful, and we lost 26.5% of our product somewhere along the way. All right, so that's it for percent yield. So I'm going to end this video and then we'll start with 8.4.